A very good afternoon, everyone. I'm Tandarani Mohanta, your host for the day, and I welcome you back to the 3D National Webinar on lithium-ion batteries and beyond, a perspective of future energy storage need. I hope everyone has enjoyed the first two talks of session 1. Now we are back with our session 2 of day 2. Our first talk is to be given by Professor Amartya Mukhopadhyay from IIT Bombay. Please kindly do put up your questions in the comment section. At the end of the talk, we will able to take a few questions. Now I kindly request Professor Partha Sahar to come to the podium and introduce Professor Amartya Mukhopadhyay to our audience.
A very good afternoon to all. It's my pleasure to introduce you Professor Amartya Mukhopadhyay from IIT Bombay. Dr. Mukhopadhyay presently professor at the Department of Metallurgical Engineering and Material Science, IIT Bombay. He completed his doctoral in material research from the University of Oxford, United Kingdom in 2009. He did his postdoctoral research at Brown University, USA for a couple of years. He is a young associate of the Indian National Academy of Engineering and presently serving as the honorary secretary of Mumbai chapter of the Indian Institute of Metal. His research interests includes materials for electrochemical energy storage, particularly focusing on alkali metal ion batteries and engineering ceramics. Among his major accomplishments, he has been awarded with the Swarna Jayanti Fellowship 2020-21, recognized by the Royal Society of Chemistry, United Kingdom journals as one of the 2019 Emerging Investigators, awarded with the IIT Bombay Research Dissemination Award 2018, INE Young Engineers Award 2016, ASM IIM North America Visiting Lecturership 2016, IIT Bombay Young Investigator Award 2014, and Dr. R.L. Thakur Memorial Award by the Indian Ceramics Society in 2013. Over to Dr. Amartya Mukhopadhyay.
Thank you. Thanks for the very generous introduction, and thanks to the entire organization team for inviting to this event. The program is very rich, and there have been quite a few very nice talks, very informative talks. Let me see what I can share with you, and I hope what I will share may help you in some way. So with this, let me share my presentation and get started. All right, I hope you can see the screen. Can somebody let me know if I am audible and if the presentation is visible?
Yes, sir. Your screens are visible and
Great,
you are audible.
thank you. Thanks a lot. So today's topic is something related to layered transition metal oxides, which are usually used as cathode materials for lithium-ion battery, sodium-ion battery, and beyond. Now, before I go ahead with the main theme of today's lecture, let me just briefly introduce my research group or the activities that we do in the group. The main focus is on electrochemical energy storage and primarily the battery materials. We think of various concepts, and based on that, we either develop modified or new materials, or play with the cell chemistry, the electrode-electrolyte interface, and from there on, we try to develop good cell and take it forward towards prototype development. In addition to that, we also work on engineering ceramics. Our major focus has been on developing ceramic alloys, while we also do some work in with like fiber reinforced and carbon graphene reinforced ceramic composites. This chart shows the wide range of activities with battery materials, while as of now, the major focus is on the layer transition metal oxides, which is in fact the topic of today. And there are fascinating class of materials, as we will soon see. And for battery perspective, they are primarily used as cathode materials, though some of the layer transition metal oxides can also be looked into as anode material. Uh, and in general, we do, as I mentioned, we do a lot of fundamental level understanding. For doing those, we need to do quite a few operando or in situ experiments and move towards a good fabrication of a good cell. We also work on solid state electrolyte, the ceramic solid state or the inorganic solid state electrolytes, and moving towards solid state lithium ion or solid state sodium ion cells. Just in case somebody in the audience may not be very familiar with the working principle of a lithium ion battery and beyond, like sodium ion battery, potassium ion battery, so on and so forth, so which can be termed as alkali metal ion batteries. So these are basically rocking chair type of systems uh, with the charge carrier ion, which is lithium ion in case of lithium ion battery system, shuttling between the cathode material and the anode material uh, during the operation of the cell. For example, during charge of a lithium ion cell, the lithium ions move out of the cathode side, which is lithium cobalt oxide or its variants, and then get hosted in the lattice of the graphitic carbon, which usually behaves as the anode material. And the reverse happens when we are discharging the cell, and that is withdrawing power stored in the cell. So as we can see, the charge carrier ion, here lithium ion, for a sodium ion cell, this can be sodium ion, and so on. They get inserted into the lattice of the electrode materials and again come out. So this insertion and removal cause a lot of changes to the electrode material. They end up changing the structure of the material in many cases, which can be good or which can be very bad. So which in turn renders this a very fascinating to look into from a material science perspective. And of course, in addition to that, a lot happens at the electrode electrolyte interface, which needs to be understood and engineered to have a good. Now, coming to lithium ion battery in a very generic sense, in a very generic perspective, what we can realize is the energy density of the lithium ion cells, they have increased, they have moved up, but the change has not been substantial, given that they were commercialized in 1990s, early 1990s, like 1991, and today it's 2022. So over these 30 years, the energy density, power density, etc., have increased, but have not really uh, but not really increased in a significant manner. The bottleneck has been primarily the cathode side. Now let me put some numbers here. The anode side, which has graphitic carbon as the active material right from the beginning of the lithium ion chemistry, uh, it stores lithium ion up to a capacity which is equivalent to 372 milliampere hour per gram. So let's take it as 400 milliampere hour per gram, or a number 400 for the anode capacity. Now the cathode capacity to start with was between 120 to 140 milliampere hour per gram. So less than half the anode capacity. Now, after a lot of work over the last 25 to 30 years, we now have cathode materials which have a capacity of about 180 milliampere hour per gram in a practical context. So, so the cathode capacity is still half of that of the anode capacity, and the cathode is still the bottleneck in terms of increment in the cell capacity and thus the energy density. So one needs to enhance the cathode capacity. In other words, being able to take out more lithium, because this acts as the reservoir. To start with, all the lithium ions are present in the cathode material. So take one has to take out the lithium ion, and the more lithium ion one can take out, the greater will be the usable capacity. And to do that, one needs to go higher and higher in the voltage range, and so one should be able to go beyond 4.3 volt, which is the present upper limit of the current generation lithium-ion cells, and maybe preferably go up to 4.7 volt if the electrolyte does not get decomposed at the same time. But going up to such a high potential does lot of damage to the structure of the cathode material, and there lies the biggest problem. Now, before trying to understand what structure of the cathode material, again, from the point of view of those who may not be very familiar with the structure of these materials, a very simplistic view can be presented here. So, what we usually call as layered transition metal oxide, the word layered, it actually refers to a cation ordered rock salt type of structure. So this is one can see that this is a rock salt structure with a cation being of two types: transition metal ion like cobalt in case of lithium cobalt oxide, or nickel cobalt manganese combination in case of lithium NMC, and lithium ion. So these two types of ions make a cation subunit cell, and the anion subunit cell is made up of oxygen. Now, in this rock salt type of structure, if the transition metal ions and the lithium ions get separated out into alternate 111 planes, one can visualize this in terms of a layered structure if one rotates the unit cell to make the 111 axis in this direction. So now one can visualize this 111 plane as a transition metal layer, this 111 plane as the lithium layer, and that is what is shown here in a way which is more commonly used to represent these layered transition metal oxides. Now, such nice ordering or layering allow facile pathway for lithium ions to move out or go in, unlike what would have happened had it been a cation disordered structure where there would have been no specific plane or layer allotted to lithium or transition metal ion. So lithium would face a lot of difficulty moving in and out from such a cation disordered structure. Now, the problem that happens with most layer lithium transition metal oxides, starting with and especially if we want to replace cobalt with some other transition metal oxide, when more and more lithium is taken out, and so the nice cation ordered structure ends up becoming cation disordered structure when more and more lithium is taken out. Now, this transition takes place via an intermediate tetrahedral site. So the nickel ion in the transition metal layer in the case of lithium NMC moves from its original octahedral site in the transition metal layer to an intermediate tetrahedral site to the octahedral site in the lithium layer. So to preserve the
Excuse
structure
me,
by
sir.
taking out more and more lithium, and that is going to high potentials, one needs to suppress this transition metal migration from the transition metal layer to lithium layer, and that is very difficult to do.
Excuse me,
So
sir.
yeah, sorry.
Sir, sorry to interrupt you, but your voice is breaking, sir.
Yeah, that may be something to do with the connectivity. So I will try to speak a bit slowly.
Sure, sir. Thank you.
Okay. So now, the one has to suppress the transition metal migration from the transition metal layer to the lithium layer, and that is what we tried to do in one of our studies, as I will show here. Now, before that, with this transition metal migration and cation disordering, slowly the structure changes from a nice layered structure to the formation of a spinel structure to a rock salt structure starting from the surface. And these rock salt and spinel structures have very minimal lithium ion transport, like they render the lithium transport highly difficult as compared to the nice layered structure. Now, if you look at this, to start with, the entire material looks nice and layered. However, after 50 cycles, the surface looks very different, and this is the formation of the rock salt structure at the surface. Now, this leads to fade in the capacity. As you can see here, if one goes to higher potential as compared to here, the fade in capacity is quite noticeable. And this also, such phase transformation also leads to cracking and delamination of the active material from the current collector. So this has to be addressed. So now, in one of our recently reported work, we tried to address this problem of cation migration from transition metal layer to the lithium layer by putting something in the intermediate tetrahedral site. Now, zinc having a D10 electronic configuration does not have preference for octahedral or tetrahedral site. So it can actually go to the tetrahedral site of the lithium layer. And that is exactly we tried to do. We substituted a little bit of lithium with zinc and found that based on the structure, based on the characterization and analysis of the structure, we found that zinc actually goes and occupies the tetrahedral site of the lithium layer, which otherwise serves as the intermediate site for the nickel migration. Now, so the presence of zinc in the tetrahedral site of the lithium layer was proven by various techniques and using various analyses. So I'm not going into too much in detail here. Rather, let me show what happens. Now, this is the undoped lithium NMC cycled up to 4.7 volt as the upper cutoff. One can see a continuous fade in the average voltage, which implies that the structure of the material, at least at the electrode, and at the same time, a huge increase in the polarization between the charge and the discharge voltage. But for the doped system, the increment in polarization is almost negligible if we compare it with this one. And so this is a first indication that the structure was more stable when zinc was doped in lithium NMC. Now, after 100 cycles, when we performed XRD of the cycle material, we could see that the cation disordering was significant in the case of undoped lithium NMC. Now, this is a signature of cation mixing. A ratio less than 1.2 is considered to be, or the lower the ratio of intensity of the 003 to 104 plane, the greater is the degree of cation mixing. And so this ratio went down from the pristine state. However, for the zinc doped material, the ratio was almost same as in the pristine state. So this is a proof that the cation mixing could be suppressed upon zinc doping, and which led to a more stable electrochemical cycling. Now, for when cycle up to 100 cycles for the undoped and the zinc doped material using a upper cutoff of 4.7 volt. Now, I should mention here that 4.7 volt is more of an academic interest because the electrolytes start degrading and a lot of capacity fade is also attributed to the electrolyte. But these are very similar cells with the same electrolyte, etc. So what one can see is with the undoped materials, the capacity fade was much more significant as compared to the zinc doped material. Zinc doped material was more stable as compared to the undoped material, and so from electrochemical perspective, this is the evidence that yes, upon zinc doping, the electrochemical cyclic stability improved in significant terms. And the reason was this, as I'd shown here, as I'd shown earlier, the zinc occupied the tetrahedral site of the lithium layer and suppressed the nickel migration from the transition metal layer to the lithium layer upon, like, when lithium was taken out from the structure. Now, this is one example of structure electrochemical performance relationship and how to tune that for the layer transition metal oxides in the case of lithium-ion system. Now, let us move to the sodium-ion system, which is expected to be a more sustainable system and especially important for a country like India, where we have a lot of sodium resources but very minimal lithium resources. Another advantage is that for sodium-ion cells, we do not need to have copper as the anode current collector. We can have aluminium, which is less expensive, on both the sides as current collector. The third advantage is that the cathode materials can work very well. They can be very stable in terms of the structure and the electrochemical performance without the need of cobalt as one of the transition ions. There are obviously a lot of problems and especially given that sodium-ion battery is still an emerging system, one of the major problem is graphitic carbon does not work as anode material because sodium ions do not get intercalated into the graphitic carbon lattice, unlike the lithium-ion counterpart. Cathode materials, again, the layered transition metal oxides, structurally they can be stable during the initial stages, but they are highly unstable upon exposure to air and water, which can which can deteriorate the structure in a matter of even minutes, as we have seen. They are highly hygroscopic that way, and upon electrochemical cycling, upon removal and insertion, they undergo lot of phase transformation changes, which also degrade the material and hence the capacity of the cathode material. So these aspects need to be addressed, and today I will focus on the second part, that is the cathode materials, and show one example. So now, when we talk about the structure of the cathode materials or the layered transition metal oxide cathode materials for sodium-ion cells, typically three types of structures can be used. Now, when we talked about lithium cobalt oxide, lithium NMC, they had this particular structure, O3 type of structure, where this O indicates that the sodium ion or the lithium ion resides in the octahedral site, whereas 3 indicates the number of types of oxygen stacking in a given unit cell. So the structure types can be denoted as O3 or P2, where P is a prismatic site where the sodium ion can reside, P3, and so on. Now, these are the two types of structure material of the structures that have been looked into as cathode material for sodium-ion battery, with some work on P3 type structure also going on. The advantage of O3 type of structure is that it can start with a sodium content of 1 per formula unit, that one can synthesize it and achieve a stable O3 type of structure with a sodium content of 1 per formula unit. Whereas for a P2 type structure, usually a sodium content of less than 0.7 leads to the P2 type of structure. But this is disadvantageous because the cathode material is supposed to be the reservoir of the alkali metal ion in an alkali metal ion cell. So that way the O3 type of structure is advantageous. Though a lot of work is now underway, including in our group, trying to stabilize P2 type structure at higher starting sodium content. But that's a different story, and I won't be discussing that today. Now, the disadvantage of O3 type structure is again the air water instability and relatively sluggish sodium ion transport as compared to in the P2 type structure. And again, both these structures undergo multiple transitions unless something is done during the sodium ion extraction insertion, and that leads to structural degradation and cycling. So, in a nutshell, we can like think of the problems associated with the layered sodium transition metal oxides as cathode material for sodium-ion battery as occurrence of multiple phase transformations and sodium vacancy ordering during sodium removal or insertion. Now, which can be addressed by multiple substitutions in the transition metal layer and leading to a smooth electrochemical, galvanostatic cycling curve, the chronopotentiogram. There can be Ion-Taylor distortion in the Ion-Taylor ions, and the presence of manganese leads to another problem in addition to Ion-Taylor distortion, that is manganese dissolution in the electrolyte. And as I told, one of the major problem is the air-water instability in the sodium layer transition metal oxides, and that can make the structure get deteriorated very, very fast, and the structure can become absolutely useless unless it is protected from exposure to air and moisture. So this air-water instability is a problem with handling because one has to minimize the exposure to air, and it also kind of mandates that the electrode preparation for which a slurry has to be made prior to putting on the current collector. So it kind of mandates that the electrode preparation, of the electrode slurry has to be done using something like NMP and PVDF, because water cannot be used to prepare a electrode slurry with these highly hygroscopic cathode active materials. So that is another big problem, because NMP is very toxic and it's not good to use it. Now, so we wanted to start by addressing the air water instability, and we selected a O3 type composition, and you can see there are a lot of substitutions in the transition metal layer, that is primarily to suppress the phase transformations that take place during the sodium ion insertion removal. Now, with all these substitutions in the transition metal layer, we could obtain phase pure O3 type of structure, and we systematically varied the manganese and the titanium content. Like one composition had 0.5 manganese, 0 titanium. The other extreme had 0.5 titanium, 0 manganese, and there was an intermediate composition with say 0.3 titanium and 0.3 titanium and 0.2 manganese. So we stepwise manner we replaced manganese with titanium to see what happens. There are logics behind that. But I will run out of time, so I'll discuss all the logics today. Now, what we can see is, for the manganese containing composition with and no titanium, the material is highly hygroscopic, and upon exposure to air for a few days, the lot of other phases starts to form, and these phases actually form when sodium ion is taken out of the structure, which means that there is a spontaneous dissociation upon exposure to air for this material, especially when it had 0.5 manganese and no titanium. Now, with increase in titanium content, the 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 the, the rate at which the deterioration was taking place upon exposure to air got reduced, and when the titanium content was 0.3, and of course when it was 0.5, the material was fully air stable even up to 40 days. One can see no change in the XRD pattern upon exposure to air for 40 days. So now we further started working with this 0.5 titanium containing material, because that was the most air stable O3 type structure that was probably reported, till date. So now this is again like seeing what happens when one uh, uh, puts it in water, a more hydrating condition, soaking and stirring. So we see that the 0.5 titanium containing material and with 0 manganese, it is absolutely stable even if it is stirred in water for 12 hours, which is otherwise a highly hydrating condition. So this material is absolutely air as well as water stable. So it does not cause any problem with respect to synthesis and handling in air, because it is air stable, and in principle one can prepare electrode using water based slurry because it is water stable. Now, there are various reasons why titanium substitution may suppress the moisture uptake. So for trying to understand that, let us first see what happens when these layer transition metal oxides are exposed to moist air or water. The sodium ion is taken out, and the water goes in. Water based species go in, and they follow the same pathway. That is, if I again show this, so it moves from octahedral site to tetrahedral site to octahedral site to tetrahedral site in the sodium layer. So spontaneous sodium extraction and water insertion takes place and follows the same pathway. When I say water insertion, I mean water based species like H plus, H3O plus. Now, with titanium substitution, what we found was that the sodium layer spacing, the sodium slab spacing, this particular spacing, it got shrunk to a little bit with the presence of titanium in among the transition metal ions. Now, when this sodium layer spacing, or this what is sometimes also known as inter-slab spacing, because these are referred to as transition metal oxide slabs. So when this spacing got shrunk, it caused hindrance to the insertion of the water-based species, and so that rendering it water stable to some extent. Now, again, titanium 4 plus is a D not transition metal ion, so it does not have a site preference for octahedral or tetrahedral site. So some of the titanium ions actually occupied the intermediate tetrahedral site. Similar to the way zinc ions had occupied the intermediate tetrahedral site in the case of lithium NMC, the previous example that I had shown. So now, if the titanium occupies some of the intermediate tetrahedral sites, then it will block the pathway for the moisture species to come in, and this further contributed towards the improvement in the water stability. Now let's see the electrochemical performance. The manganese containing material, with no titanium, it showed a very poor performance. One can see decrease in capacity and increase in polarization very rapidly during cycling. And one could also find presence of manganese in +3 state at the surface, which is very bad because it can disproportionate into +2 and +4, with the +2 getting dissolved into the electrolyte. So it's a mess with so much of manganese. Getting a stable, electrochemically and structurally stable layer transition metal oxide is actually very, very difficult, and that was again shown by our material. Now, when we had titanium and no manganese, as in this case, we could see almost no increase in the polarization up to 100 cycles, and all the ions were stable in the oxidation state they were supposed to be. And in terms of cyclic stability, it showed a very, very good cyclic stability compared to the 0.5 manganese 0 titanium containing counterpart. Now, to increase the rate capability, we mixed it with carbon nanotube, and that could drastically improve the rate capability as well. So this material can be used for a stable cell performance, stable sodium ion cell performance, and also draw quite a high current if one mixes it with a little bit of carbon nanotube. Now comes the most important part, that is, okay, fine, we kind of established that this cathode material is water stable, but can we prepare an electrode using water based slurry and not use NMP? Now we did that. So this is the cyclic stability offered by, or exhibited by, the cathode material, which was prepared using a water based slurry. I mean, the cathode prepared using water based slurry, and one can again see that it is fairly stable, even though even though the electrode was prepared using water and there was no NMP used in the electrode preparation. So this is an important development because one has obtained a sodium transition metal oxide based cathode material which is very stable in air. So no need to run to a dry room or humidity controlled atmosphere for synthesis and handling of this material. And one can even prepare electrode or cathode using a water based slurry and have a stable sodium ion cell cathode. So this is the summary of that particular work. So one can see the comparison between NMP processed and water processed electrode. So this is up to 200 cycles, this is up to 750 cycles, and one can see hardly much difference in terms of the cyclic stability between the NMP processed and the aqueous processed cathode material. Now, as a next step, we of course move towards the cell development. So we prepared another layer transition metal oxide, which is a slightly modified sodium titanate. It's a biphase sodium titanate, and which also showed excellent cyclic stability and exceptional rate capability. One can see even at 50 C, one can get a very good stability and very good capacity. So presently we are clubbing these two materials and trying to develop a full cell based on these two, full sodium ion cell, and then proceed towards prototype development. So with this, I will end my talk. Let me acknowledge the funding agencies and my collaborators for all the contributions, and special thanks to the students for the encouragement they provide and for doing a lot of hard work. And it's because of them I can present something like this in front of you today. So, and thanks to all of you for listening to my talk. Thank you.
Sir, we have a question from one of our audience. It will be displayed on the screen.
On the screen. Now, which question? Oh, Yeah, Siddharth Nanda, right? You mentioned titanium substitution enhances the water stability of the material, but it is also helpful in solving problem associated with manganese 2 plus dissolution and Ion-Taylor distortion. Yeah, that is correct. So when we do not have manganese, obviously the manganese dissolution and Ion-Taylor distortion goes out of question. But as you also rightly, I mean, I think you rightly pointed out that if even if we do not want to get rid of the entire manganese, if we have part substitution of manganese with anything like titanium or something, it can uh, it can still suppress the manganese dissolution, and especially it can render the Ion-Taylor distortion as to be at not a long range Ion-Taylor distortion. So it can minimize the overall distortion of the structure even if we substitute part of manganese with something else. So very nice question. Now again, as you also mentioned, the layers for shrunk that is immediate. Yes, that's a very good question. Yes, it does. Yes, it does affect the sodium ion movement as well, and accordingly, you did see for that material the inherent rate capability was not really good. So two things: one, the layers shrunk, so the sodium transport becomes hindered, and at the same time titanium 4 plus it's a d naught transition metal ion, so it also hinders the electron delocalization in the transition metal layer, so that also reduces the electronic conductivity. So combination of these two effects lowers your rate capability. Yeah, so if one wants to achieve something, the other gets compromised to start with, then one has to come to a compromise between both the two things to achieve, I mean, a little bit of this and little bit of that. So that always happens. Uh, any other question?
Okay, very good afternoon, Professor Mukhopadhyay. This is Dr. Shah. It was
Yeah,
nice presentation.
thank you.
Specific questions regarding your zero manganese, 0.5 titanium, water and air stable sample. You mentioned it's very electrochemically stable, giving a decent capacity and stable up to 100 cycle. I was wondering, like, when you're trying to extract sodium, because this is a layered oxide, O3 type layered oxide. So what is actually happening in the structure? Because all these magnesium, copper are electroinactive, even including titanium. So if your sodium comes out, how the structure retains its, I mean, how the structure is being retained? Because there is no redox couple, it appears
No,
to
no,
be.
yeah. Sorry. I did not stress upon it. Yeah. So I got your point. I did not stress upon it. But if you refer to the, yeah, sorry. If you refer to the composition, you can see there is nickel. So nickel is the primarily the redox active transition metal ion. So the composition, I can just put the composition in the chat box. Let me put it. Oh, so this is the composition. So you can see there is nickel in that, which is primarily the redox active ion, and also copper is in +2 state. So at high voltage, copper can undergo +2 to +3 change in oxidation to take care of further sodium extraction. Hello, hello.
One query.
Am I audible?
You mentioned about cation mixing effect in
Hmm.
your initial NMC 111, and you
Right.
indicated that the ratio 1.2, more than 1.2, there is less cation mixing, and if the ratio of I003 by I104 is less than 1.2, then there is a cation mixing. So, can you explain this? What is the reason behind this ratio, and how actually it helps
Oh,
to
that
understand
okay.
material scientists? Like, if you are developing a material, let's say I am substituting nickel with other transition metal or some electronegative metal, how this ratio of the relative intensity ratio, which is actually obtained from the XRD data, can help to understand that the material will have less cation mixing. Another case, it might have high, it's prone to high cation mixing. So,
Right. Uh, fantastic. So that comes from very basic of XRD. So it is related to the structure factor associated with the two planes. Now, in one case, you have a difference between the atomic scattering factor of lithium and transition metal, and in the other case, you have a summation. So, when the transition metal goes into the lithium layer, change in structure factor is such that the 003, not much change happens to the 003, but the 104 becomes strong, gets stronger. In the intensity of 104 becomes stronger, and so the ratio between 003 and 104 goes down when you have uh, the transition metal which have a higher atomic scattering factor move to the lithium layer. So it is totally based on this, like a combination of atomic scattering factor leading to the structure factor. Hello, am I audible? Hello. Hello, hello,
Hello,
hello, hello.
hello, sir. There's one more
Yeah,
question.
yeah, sure.
The question is displayed on your screen, sir. Can you
Oh,
please
question
confirm
is
it?
on my screen. Graphitic carbon, is it due to the is not usable? No, it is not due to the difficulty in sodium ion insertion as such. Uh, at least not related to the size of the sodium ion compared to lithium ion, which is usually thought about, because like one can immediately realize that lithium ion gets intercalated, sodium ion does not get intercalated, but potassium ion can get intercalated. So it is definitely not the size. It is primarily due to the fact that sodium ion does not get what I will say. So the interaction between sodium ion and graphenic carbon is such that that sodium ion does not like to reside on the surface of graphenic carbon. So of a pure graphenic carbon, I mean of a defect-free graphenic carbon. So that is the reason why graphenic carbon does not host sodium ion. It's nothing to do with the size as such. Yeah. Next question.
Thank you, Professor Amartya Mukhopadhyay, sir. Uh, you have clearly explained all the different aspects of sodium-ion batteries involving layered transition metals, and I hope my all the participants must have enjoyed our talk. Now, I kindly request Professor Ranabratam Majumdar to present the memento to Professor Amartya Mukhopadhyay.
Okay, good afternoon. So I want to congratulate Professor Mukhopadhyay for his nice presentation. So I have one just before giving the memento. I have one question that this preparation of this sodium bearing this kind of cathode material, any problem in maintaining sodium stoichiometry in the final compound? Are you facing any problem?
Yeah, it is always there. So not as bad as lithium, but sodium is still volatile. So one always has to have a little bit of sodium excess, and that sodium excess also has to be optimized. So that is one. Second is there is a problem with nickel, because nickel always tries to go to its +2 oxidation state. Now, unless the stoichiometry is maintained very precisely, that the nickel will be in the oxidation state that is desired. If there is a little bit of mistake, so the nickel will try to go to its +2 oxidation state and come out as nickel oxide. So that is another problem which one faces with nickel. So yes, the sodium excess that is taken to minimize the sodium, or to take care of the sodium loss during the high temperature treatment, has to be very precise and has to be optimized.
Okay, thank you. On behalf of the organizing committee, we are presenting a memento to Professor Mukhopadhyay, so kindly accept it. And this memento is basically, so our institute is in the tribal belt, so that tribal day-to-day activity, which is that is painted on a palm leaf, so that will be sent to you by post.
Great. Thank you. Thank you very much. That is very kind. Thank you.
Thank you, sir. You can leave the session now.
Thank you.
Thank you to our audience for patiently listening to the last talk. Our next and the last talk of the day 2 will begin at 4:20 p.m. by Professor Shobhit Omar from IIT Kharagpur.
No,
Excuse me, sir. Excuse me, sir.
Hello. Yes.
Welcome to the 3-day national webinar, sir. We will be starting
Thank you.
within 2 minutes.
Okay, sure. Can you see my screen?
Yes, sir. Your screen is visible.
Okay, that's good.
Uh, can you please make it a slideshow, sir?
Yes.
And we will be giving a brief introduction of yours, and after
Sure.
that you can start your session.
Right.
Good afternoon, all. Now we will begin with our last talk of the day, day two. Our last talk is by Professor Shobhit Umar from IIT Kanpur. I request all the audience to kindly put up their questions in the comment section. Now I kindly request Professor Ranagata Majumdar to introduce Professor Shobhit Umar to our audience.
Good afternoon. It's my pleasure to introduce Professor Shobhit Omar. Dr. Shobhit Omar did his BTech in ceramic engineering from IIT BHU. He has earned his MS and PhD degree in material science and engineering from the University of Florida. As a postdoctoral researcher, he has spent a few years in Raiso National University, Denmark, and Shibuka, Japan. In 2011, he joined as an assistant professor in the Department of Material Science and Engineering at IIT Kanpur. He is currently an associate professor in the same department. He has also worked as a visiting faculty in Material Science and Engineering department at the University of Maryland, USA from 2015 to 16. Dr. Omar's research involves studying the electrically conductive properties of ceramic materials, defect chemistry in metal oxide, establishing structure property correlation, solid oxide fuel cells, and batteries. He has authored several research articles in the international journals related to energy materials. I am requesting Professor Omar to start his presentation.
Thank you for the kind introduction. Good afternoon, everyone. So I hope you can hear my voice, right? Okay. So I will be presenting on solid state sodium ion batteries, right? So this whatever I'm going to show is a work that has been done in my lab, Um and so we'll be focusing over the solid state sodium ion battery where you require a solid electrolyte. And in this presentation, I will be more focusing over the ceramic based solid electrolyte. Okay, but we will talk about a cathode material as well, which is also a solid base. So let me start with the presentation. So batteries, as you can see, that they are used to supply power backup in a wide array of applications. I don't want to spend much time here, but because this seminar series is on batteries, so you know the importance of batteries and what are those applications. You can see that it is predicted that the battery market is going to increase from 92 USD million in 2020 to 152 USD billion by 2025, and it's mainly because our adoption of electric vehicles and also the use of renewable energy. Right now, government is hard pushing towards the use of renewable energy, and that is where it becomes very important to work over viable, efficient, and cheap battery.
Excuse me, sir.
That Yeah,
Sorry to interrupt you, sir. Can you please confirm that the slides are moving? Are
yeah,
you
it is
changing any
moving.
slides?
Yeah,
Sorry,
I'm
sir.
changing my slide.
We couldn't
Are you not
view
seeing
your.
the second slide?
Yes, sir. We aren't able to see your second slide.
Okay.
Yeah,
Uh,
it's visible now, sir. It's visible now.
but I'm putting in this now. What about now?
No,
Can
sir.
you see that?
No, sir, you have chosen the slideshow option, but it isn't in the form of a slideshow.
Okay. What should I do then? Let me just then keep it like that, right?
Okay, sir,
Is that okay
that's
with
fine.
you?
Yes, sir,
Are
it's
you able to see
absolutely fine.
this?
Yes, sir, we are able to see that.
Okay. The only problem is I cannot use the annotation. Okay, that's right. So you can see that we have to develop viable, efficient, and cheap batteries for the energy storage. And here in this schematics, one can see battery is an important cog of renewable energy wheel. It can produce clean energy, it can use the renewable resources, and of very important thing is it can supply a continuous supply of energy, because most of the renewable energy is from the solar energy or wind energy. They are intermittent in nature. So we can store this excess energy and we can use it whenever it is required. So that's the importance of the battery technology. And we have to make we have to develop viable and efficient batteries for this renewable energy systems. Now, two types of batteries are very commonly discussed, and of course, lithium-ion battery, which when it was developed and commercialized in 1992 by Sony, it has been widely used for a wide array of application. All I think most of the consumer electronics are from the lithium-ion batteries, but the problem rises because of the expensive lithium mineral resources, and of course it is present in politically sensitive locations. So we have to look for the alternate chemistries, and among most of the chemistries that are there, sodium is the most exciting. It's because it's earth abundant, and of course this is inexpensive. Here are certain physical property which are compared for lithium and sodium, and one can see that lithium and sodium show very close resemblance. Of course, lithium has a very low potential, and sodium has it's next to lithium. Of course, that will affect the energy density. But you can see the crust abundance of the sodium is far, far greater than for lithium. And of course, the cost is very low compared to lithium. So sodium ion batteries provide a less volumetric and gravimetric energy density, but it is very much suited for large stage energy storage application. And while designing the batteries, we have to look for different type of factors like it should be environment friendly, easy to fabricate, chemically and thermally stable, high energy density, power density, durable, and cheap in nature. Right? For grid storage application, energy density or power density is not a big crucial factor, right? Mainly the energy density is not a crucial factor, right? So that's why the sodium ion battery come into the picture, because of course the even the capacity is not as much as lithium, but it is cheap, and the sodium reserves are easily available, right? So here are certain requirements for cathode, electrolyte, and anode materials, and you can see that for the cathode and anode, you require a redox couple in both the cases. But for the cathode, it should have a high redox potential, while for the anode, it should have a low redox potential. Okay, and both should have a high specific capacity, while the that will improve the energy density of both cathode and anode, and uh, it should be conducting for both sodium and electron in both the cases, cathode and anode. And when you look over the electrolyte, it should be that materials, electrolyte materials should be compatible with the cathode and anode. That's a very crucial requirement. And it should be sodium ion conducting, and of course, it should be electrically insulative in nature. So to let you know, there are two type of conduction that occurs. One is ionic conduction, the other is electronic conduction. So the electrolyte should be sodium ion conductive, and it should be insulative to all type of electron conduction. The fourth important thing is that electrolyte should be should have a wide range of potential stability window. Okay, the stability window should be very large so that it can take a high potential cathode material, right? If the if you are working with a high potential cathode material and your electrolyte have a low potential stability window, then you cannot go to high potential, because before going to the high potential your electrolyte will break down. So you want to have such type of electrolyte which has high potential stability window. So there are different type of electrolytes that are used, and in this presentation I will be mainly talking about the solid electrolytes, and that is also based on ceramic. Okay, but before going into that, I will be discussing about the cathode material, which is very important to in solid state sodium ion batteries. So here are the comparison of the potential and the capacity of various type of material that have been used for sodium ion batteries, right? And one can see there are two class of material. One is here, the other one is here, right? Low potential material, and these are high potential material. So high potential material are used for the cathode, and the low potential are used for the anode application. Okay, and one can see that anode have a very high capacity compared to your cathode material. So the capacity of the cell will mainly depend upon the capacity of the cathode, because if you have very low capacity of cathode, right? So the capacity of your whole cell will be dependent upon this material, what type of material that you are using. So ideally, we would like that we have to develop a cathode material which should lie here, somewhere here, right? It should have high capacity and should have high potential. Okay. Now, this Na3V2PO43, which has a Nacicon structure, is widely used as a sodium ion battery cathode. Okay, and let me tell you, there are different type of cathode material that are used, like layered metal oxide, like layered or tunnel metal oxide, and then you have this polyanion Nacicon based cathodes, as well as you have sulfur cathode, and then there are other cathodes based on this olivine structure as well. So here I'm going to talk about the Nacicon structure, because Nacicon structured cathode, because our electrolyte will also be of Nacicon ceramic base. Okay, so let me discuss about the structure first. So Nacicon Na3V2PO43 is a polyanion compound, and it provides a 3D open framework structure where you have a interconnected interstitial spaces through which the sodium ion can move around. And here is the structure of Na3V2PO43, and you can see vanadium is forming a octahedral like this, while phosphorus is forming a tetrahedral, right? And each octahedra is connected to 6 tetrahedron, right? And there are 2 sodium sites in the Nacicon structure of Na3V2PO43, which is known as Na1 and Na2. These are 2 crystallographically different sites. Okay, they are not equivalent. They are 2 different sites, and one can see that this is a rhomboidal structure, and here Na1 is basically present between the 2 Laltane type structure. This is a Laltane type structure, what we call, and it's called M2PO43, and this sodium one side is present in between the 2 adjacent Laltane structure, whereas Na2 is present between the 2 adjacent Laltane structure. This is one ribbon type structure, right? So Na2 is present between the 2 ribbons, while Na1 is present between the 2 Laltanes. Okay, so this is how you describe the Nacicon structure of NVP, I should say. Also, the diffusion mechanism involves the both Na1 and Na2, and it is called a concerted ion exchange diffusion process. What do you mean by concerted ion exchange process? It means that two sodium ions are going to jump at the same time rather than one single jump is occurring, right? So it require a vacancy, right? It require a vacancy. So the jump will only occur when there are two sodium ions are moving in the at the same time. So that's how the diffusion occur in this type of process. And this is basically seen through computational study. And we will talk more about it when we talk about the electrolytes. So diffusion occur from Na1 to Na2. This is the diffusion channel and how it occurs. And you can see that if you can improve the sodium ion conductivity inside this material, then you can basically use this material at higher current rate. It can give you higher power density, right? What we had done, we have tried to dope this NVP material, and we did it by doping through silicon on phosphorus side. And why silicon? Because it has a similar ionic radius as phosphorus, so little bit larger than phosphorus, so it will expand the lattice, and that is what we are trying to do. We are trying to increase the interspatial channel space, and also we are trying to increase the concentration of sodium ion inside this material. Okay, so we tried to synthesize the nano-sized powder of NVP doped with silicon, and different type of compositions are prepared, and these are prepared to solve the route. Uh, the process is already shown here. We have used citric acid as a chelating agent, and this citric acid not only work as a chelating agent, but it also provide a residual carbon inside this material that will increase the conductivity, electrical conductivity of this material. So here are the XRD of synthesized powder. You can see that NVP is basically x equal to 0 is basically your Nacicon structure, and Rhomb-Buttel Nacicon structure, and you add some 0.1 and 0.2, and there are no such impurities present in these compositions. But at x equal to 0.4, there are some impurities peak present in this material. So one can see that there is some solubility limit of silicon inside this NVP, right? And if we have also calculated the unit cell volume, and we have seen a linear increase in the volume as we add silicon inside the material. So if you look over the Raman spectra that we have done over these silicon dope composition, we can see that there are two peaks which are important, which are D and G band, right? This one, and of course this one. So these two show that there is some residual carbon present inside the material. And when we did the TGA, we have found that there is a loss of 11.8% weight loss in this residual, which is mainly associated with the residual carbon. And when we looked over the high resolution TN, we observe a coating of around 10 to 15 nanometers over the particle of Nacicon particles of NVPS. Okay, now this coating will help to give electrical conductivity inside this material. So it will act as a current collector. So we fabricated a coin cell using this developed NVPS material, and you can see the morphology of NVP, and we have used the CNT as an additional conducting agent. We use PVDF as a binder, and which is dissolved in NMP solvent. And slurry preparation was done, and then we cast this slurry over the aluminum foil, and we dried it, vacuum dried it, and then purged the cathode from the this coating. So this is the coin cell fabrication assembly, and one can see that this is a sodium that we have used, and this is a separator, glass filter separator, and here you have an electrode which we can call as a working electrode, which is basically your NVP coated on the aluminum foil. And we crimped it to prepare this type of coin cell, and all this assembly was done inside the glove box under the controlled oxygen and H2O traces. Let us talk about the electrochemistry involved in these type of coin cell. Okay, so first what we did was to measure the cyclic voltammetry of these half cells, you can say. And if you look over this NVP, NVPS 0.1 and 0.2, you can see the cathodic, which is this is your cathodic peak and this is your anodic peak, right? Anodic peak. There is a difference between the cathodic peak and anodic peak. Okay, and you can see that the peak separation for NVP is around 0.153 volts, while for NVPS 0.1 and 0.2 it is 0.103 and 0.084, which means that you are moving more towards there are more polarization losses involved in NVP compared to NVPS 0.1 and 0.2. Okay, so that is what we want, that the polarization losses should be less and the material should be more towards the reversibility region. Okay, and we have performed the CV at different rates, and you can see that this peak intensity increases with the increase in the scan rate, and also this gap increases. Okay, and this gap, the increase in the gap is basically mean that we are in the quasi-reversible region. That means the electrochemical reaction that are occurring at the working electrode is quasi-reversible in nature. It's not completely reversible and it is not completely irreversible. It is in the quasi-reversible state. Now, if we now reversibility depend upon the what scan rate that we are doing the CV, cyclic voltammetry, right? And Rendel's cyclic equation is very important equation which relate the peak current with the scan rate. And here I have plotted the peak current as a function of square root of scan rate, and you can see that you got a linear line, right? But this data point deviates from the linear point at around 0.25 millivolt per second for NVP case. On the other hand, for NVPS 0.1, it remained linear till 1 millivolt per second, while the same thing happened for NVPS 0.2. What it means that this NVP remained reversible till 0.25 millivolt per second, while the reaction in NVPS 0.1 remains stable, reversible till 1 millivolt per second, right? So so silicon doped NVP exhibit reversibility at much higher scan rate compared to your NVP cathode. We have also tried to calculate the diffusion coefficient of sodium ion using this again the random cyclic equation, and we observed that the NVPS 0.1 show higher diffusivity compared to your NVP cathode material. Now look over the electrochemical performance this half cells that we have prepared. So here you can see that of course at different current rate, which is C by 10, 1C and 5C, you can see that the polarization losses is increasing as you increase the current rate. And NVPS cathode show higher capacity compared to your NVP cathode, right? And this happened at most of the current rate that we have tested. Also, you can see that we did cyclability performance at 1C rate, and we can see that only 15% decrease in the discharging capacity in NVPS 0.1, while it was 23% in the case of NVP cathode. Okay, so Coulomb peak efficiency also reached 100% only after few initial cycles. On the other hand, it took longer cycles to reach 100% for the NVP system. If you compare the rate capability, as I showed in the previous slide, the capacity retention is higher for NVPS cathodes compared to NVP cathode, and this happened in most of the current rates that we have tested. We have tested till 10C rates, and then we again go back to C by 10, and we are able to again recover that capacity in NVPS case. Okay, so NVPS is the most basically the optimized composition that we have obtained. So based on this, I can summarize that NVP is a excellent structural stability cathode, and its capacity and electrochemical performance can be improved by doping phosphorus by silicon, right? Because that will increase the sodium ion concentration and also expand the crystal lattice, that will help the sodium ion to diffuse faster inside the material. So here I talked about the cathode that is based on nacicon. Now let us talk about the nacicon based electrolytes. Okay, and that is also ceramic, right? So finally what we will do is we are going to use this cathode of nacicon base that we have developed, and also the developed solid electrolyte, and we will see what is the performance of the solid state sodium ion battery. Now look over the solid electrolyte that are commonly used for sodium ion batteries. So first let me tell you that most important electrolyte that we use in the sodium ion battery is the polycarbonate dissolved in the some type of organic solvent, and that is the liquid electrolyte, and this is normally used in the conventional battery cell, and the conductivity of this liquid electrolyte is around 10 millisiemens per centimeter, right? 10 millisiemens per centimeter. Now the highest conductivity that we can obtain from the solid electrolyte is around 1 millisiemens centimeter. So there is the gap of one order of magnitude between the solid electrolyte and the liquid electrolyte. Okay. Now, what are the advantages of the solid electrolyte? Is these solid electrolytes are non-flammable, they are non-toxic, they can go for longer cyclic performance because there won't be any dendrite growth inside the material, and also they can give you higher energy density. How? Because they have a potential window which is larger. So you can basically use higher voltage cathodes with the this type of solid electrolyte. And of course, since they provide a physical barrier, you do not require the separator in the battery cell. Okay, so there are different type of solid electrolyte which have been tested for sodium ion battery, and here I have classified them. First one is the polymer base, which are used like PEO, right? But the problem is it show very poor ion conductivity, sometimes in the range of 10⁻⁵, or I can say 0.01 millisiemens centimeter. So if you want to increase the conductivity of polymer, you have to increase the temperature of the battery cell if you are using the polymer based electrolyte. Now comes the sulfide based electrolyte. Now sulfide based electrolyte, recently it has been said that it can reach above 1 millisiemens per centimeter, the conductivity for that, right? So this is very promising. But the problem with sulfide based electrolyte is that these are very much sensitive to the atmosphere, right? They can easily react with the moisture, and then the performance degradation will occur. So any type of fabrication that you have to do with the sulfide base, you have to do inside the glove box, inside the inert gas atmosphere. So that's a problem with the sulfide based electrolyte. The other one is the oxide base, which I'm going to talk today. The first one is a beta alumina, which has been known for a long bit of time, and this beta alumina is also used for high temperature sodium sulfur battery that operates at 300 degrees centigrade. Beta alumina is a very good sodium ion conductor. It can give you a conductivity of 2 millisiemens centimeter. Please remember, this is 1 millisiemens. It can give you around 2 millisiemens centimeter per at room temperature. problem here is in order to get the beta alumna conductivity of 2 millisiemens centimeter, you have to go to high temperature for sintering. That will be around 16 to 1700 degrees centigrade. So that's a major issue with the beta alumna. However, recently some paper has come that using cold sintering process, you can lower the sintering of beta alumna, and that is very exciting. Basically, you can use this material for solid state sodium ion battery. Now, one other challenge is the conductivity is two-dimensional only, right? It has a two-dimensional conductivity. It is not three-dimensional one. Okay. Now, the Nasikon electrolyte, which I'm going to talk in today's lecture, we will go in the next slide from here. Okay, and the other class of material that are that is exciting is a ceramic polymer based composite, which I also think is a way forward. Right, we have to use the positive attribute of both ceramics and polymer and try to make a composite type of electrolyte and use that for solid state sodium ion battery. So let me look into the Nasikon structure sodium electrolytes, right? So the first Nasikon chemical composition that compositional series that have been tested is basically given by this, right? You can see this is developed in 1976 by Hong, but not much work has been done since then. But this room temperature sodium ion battery, solid state sodium ion battery came sometime only in the last decade. Much research has been done over it, and this material has again received much popularity, right? And significant research attention has been given over this material only in the last decade, right? So several type of cation is doped in this Nasikon and try to evaluate how the performance is. Okay, and so these materials have been synthesized in a wide variety of ceramic processing route, and these are the different structures that are being reported for the NJSP material, but most common structure is monoclinic and rhomboidal structure. Right here, it's given the rhomboidal structure, and this is the monoclinic structure. Right, and you can see in the rhomboidal structure, which I have also discussed in the when I was talking about the NVP. It also is a rhomboidal structure. It consists of two inequivalent sodium site, that is Na1 and Na2, and diffusion occurs from Na1 to Na2 to Na1. This is how it occurs. And in one formula unit, you have one sodium site, Na1 site, and three Na2 sites. Okay. Now, what happens is in the monoclinic structure, these three Na2 sites break into one Na2 and two Na3 sites. Okay. So now you have three different cryptographically different sodium site, Na1, one Na2, one Na2, and two Na3. Okay, right? So these two structures are very important structure, and most of the paper are reporting these two structures. Okay, and you can see that rhomboidal phase is a high temperature phase, and above 160 degrees centigrade, you get the rhomboidal symmetry, and this symmetry is lost if you cool down the rhomboidal phase, transform to monoclinic phase if you cool down this material. But you can also stabilize this rhomboidal phase by doping the material with some type of cations. Let's talk about the conduction mechanism. And as I said, that in the rhomboidal structure, the conduction occurs from Na1 to Na2, then to Na1, while in the monoclinic structure, the structure both Na1, Na2, and Na3 sites are involved in the conduction mechanism. Recently, in 2019, there is a paper by Zhang who had done the computational study over the conduction mechanism in the rhomboidal and monoclinic structure. It was said that correlated diffusion process is preferred compared to single ion hopping. That means that two sodium ions should jump at the same time compared to one single ion hopping. So correlative diffusion process is dominant in these materials. Another important aspect that you can see that sodium ion are moving through one side to another through a channel, but they are also passing through a bottleneck, which is a geometrical constraint. Okay, and these are given by T1 and T2, right? T1 and T2. Now, if you increase the size of this T1 and T2, you can expand the lattice, and you can promote the ionic conduction inside the material. Okay, so here are certain factors which are involved, which will affect the conductivity of nacetone. First one is, of course, the chemical composition. What composition you are working with? What are the phase formation? Now you can see it can be rhomboidal, it can be monoclinic, right? Now you recently there was a computational work by Ren et al., where they have found that the rhomboidal phase is more conducting, at least 1 order of magnitude more conductive than the monoclinic phase. Okay, so rhomboidal phase, if you somehow uh, stabilize to room temperature, that will increase the ionic conductivity inside the system. Okay, of course you can expand the lattice, you can modulate the size of the bottleneck, you can increase the sodium ion concentration, and of course since this is a hopping mechanism, you require some vacant interstitial site through which the sodium ion can jump and diffuse through the material. So you require some vacant sites. So in this work, what we did was we used magnesium as a dopant, okay, to dope in this compositional series. And why magnesium? Because it's cost effective, it's easily available, and its ionic size is very much close to that of zirconium. So we are trying to dope magnesium in the zirconium side, and at the same time, what we are doing is we are doping silicon in the phosphorus in this particular ratio, because that will increase the sodium ion concentration inside the material. So you can see it is right now 3.2 plus 2x, right? So let us see what happened. So we fabricated all the standard electrolyte using the solid state reaction method. So I will not go into detail about it, but we got all the pellets that are more than 90% of theoretical density, right? So these are the phase formation, and one can see that you get a monoclinic phase in all the composition, right? But you also observe some rhomboidal phase formation, and I will discuss about it here. Okay, but you see that monoclinic zirconia is present in all the composition. In all the composition, some monoclinic zirconia is present, and they are present at the grain boundary. Of course, that is detrimental to the grain boundary conductivity, right? But you can also observe that from 0.128 onwards, you are having some small peak of Na3PO4 phase. This phase is basically is also containing some magnesium, because this has been earlier reported as well. Now come to this figure, right? And this is the magnifying view of XRD pattern, and this is basically this peak that I'm magnifying here, right, near 90 degree. And you can see that this middle peak in the monoclinic phase, there is a middle peak present, and this middle peak is disappearing as you increase the concentration of magnesium inside the material. Okay, now this disappearance is basically showing that we are partially transforming the monoclinic phase to the rhomboidal phase. Okay, so there is a good thing about adding the magnesium. We are basically stabilizing the rhomboidal phase at room temperature. Now look over the microstructure of these samples that we have prepared. We can find that the big large porosity is present in NJSP, while other compounds do not have such type of pores. Okay. Another thing is that NJSP material is pure, and bare NJSP is do not have lot of liquid phase present, and this liquid phase is between the two grains, right? And this liquid phase is also present in 0.028 and 0.078. But in 0.128, there is a negligible amount of liquid phase present in this composition, right? And in 0.178 and 0.228, I do not find any type of liquid phase present in this material. However, as you go to higher composition, magnesium content composition, you can find intragrain cracks present inside this material. We also observe some cracks along the grain boundary. This is detrimental to the conductivity of this material. So we feel that this is basically happening because of the anisotropic thermal expansion, and also it's because of the absence of liquid phase symmetry. Okay, because liquid phase do not, it provides some cushion, and this cracks are not generated at lower magnesium content material. When we look over the BSE images, we found some secondary phases present in the microstructure, and these phases are basically because of the phosphate, sodium phosphate or zirconia. But we cannot able to distinguish between these two because they have the similar binding energy, and so EDS cannot differentiate between these two type of phases, secondary phases, which are present in a higher composition material. When we did impedance spectroscopy to understand what is the conductivity of these solid electrolyte, okay, and this is our room temperature sample holder, and we place our sample here, and then there is a above piston and the bottom piston, and we place our samples electroded sample, and we did the impedance spectroscopy. Of course, at room temperature, we are not able to observe the grain semicircle, but we have observed a partial grain boundary semicircle, and from there we are able to get what is the total ionic conductivity of this material. Okay, this is basically the done at room temperature, but we also did at 0 degree centigrade as well. So we plotted the Arrhenius plot, and but this figure is important. You can see that conductivity increases with increase in the magnesium content, and then there is a decrease in this. This increase is basically because of the increase in the excess sodium amount in the material, and of course, so 0.128 structure is a composition have the optimized microstructure. It do not have any liquid phase, and of course, there is a negligible cracking, which is also not there, right? And of course, there is a decrease in the density, right? This will also have an effect on the conductivity that you are observing for 0.128. So you can see there are compounding effect of various factors, like density is also there, secondary phases are there, primary phases which are forming. So, and the magnesium sodium amount which are present inside the crystal structure. So that will have a effect on the conductivity that we have obtained. But you can see that when we are able to consistently obtain a conductivity of 3.2 millisiemens per centimeter. We started from 1 millisiemens per centimeter, but we are able to achieve 3.2 millisiemens per centimeter at room temperature, and that is also using earth abundant magnesium. We did the this galvanostatic cycling performance testing at different current rate, and we got a stable cycling performance. So you can see that this is at the 125 cycles we did at 0.5 milliampere per centimeter square, and then we again gone back to 0.0 milliampere per centimeter square. We got a stable performance, that it shows that there is a excellent sodium dendrite separation capability of these electrolyte material. Then we fabricated the solid state cell. Okay, what we did first, we have first used the sodium as a metal, as an anode, and this NVPS cathode that we have prepared, right, fabricated there, we have used, and then this solid electrolyte that we have prepared in our work that we have used. We press the sodium metal over the and spread the sodium metal on the ceramic pellet, and we use a coated NVPS electrolyte cathode, and to improve the interface between the solid electrolyte and the cathode, we add a few drops of liquid electrolyte. Okay, so that will increase the uh, transfer, sodium ion transfer between the solid electrolyte to cathode. We measured the impedance spectra of this, and we have obtained the conductivity of 3.04 millisiemens per centimeter, which is again showing that this is very consistent to what we have obtained from the earlier work, that is 3.2 millisiemens per centimeter. We did the cyclic voltammetry of that cell, and we have obtained that this CV, this is the oxidation peak and this is the reduction peak, which is very close to each other, and this is very close to 3.4 volts, and this is basically represented V3 and V4 plus redox curve. We did the rate capability performance testing, and we have obtained a discharge capacity of 95 milliampere hour per gram at C by 10 rate. However, the capacity deteriorates at higher current rates. And there are two reasons for that. First one is that we are pressing the sodium on the ceramic electrolyte, and that interface is not very good. The other is basically we are still having a low ionic conductivity electrolyte, solid electrolyte. We did the cyclability testing at C by 10 rate, and the performance was very much stable till 25 cycles. You can see. So solid electrolyte works very well at C by 10 rates. Then we have prepared the symmetrical cell, which is the full cell. Okay. Till now I have used the anode, which is made of sodium, right? But now we have used NVPS as cathode as well as anode. Okay. You see this V3 and V4 redox couple is used for cathode, while V3 plus and V2 plus redox couple is used as anode. Here you are getting this reaction occurring at 1.6 volts, and this reaction is occurring around 3.4 volts. So you can basically get cell voltage around 1.8 voltage. Okay, so that's what we are trying to do. So we basically test this solid state battery at okay, and we got a initially the performance was not very good. So it was around 65 then, but then it activated, and then you get a stable performance till 71 cycles. It was the performance increased till 75 to around 65 milliampere per gram, and also the Coulombic efficiency is above 90%, right, in most of the cycles. So this is the conclusion of this work about the electrolyte. We have used the magnesium, which is earth abundant, which is cheap, and that can be used for solid electrolyte in sodium-ion battery. And of course, there are other reports, 2-3 reports, which say that one can improve the conductivity to 4 to 5 millisiemens per centimeter by using the scandium elements. But you know, scandium is mostly compared to magnesium. It's not easily available as well. So magnesium is the way forward for the Nasikon electrolyte. We have used the low cost synthesis, and we have optimized composition. It's an optimized microstructure, and the conductivity we have obtained is 3.2 millisiemens per centimeter. We feel that it's because of the low grain boundary resistance, and because of the decrease in the liquid phase entry. It has high sodium ion transfer number around 0.99. It has a wide potential stability window to 0 to 6 volts, and it has an excellent sodium dendrite suppression capability. And of course, the solid state performance is very good, but we still have to work over how to improve the interface between the solid electrolyte and solid cathodes. Finally, the acknowledgement. This work has been done by multiple students to my postdocs. And my postdoc, Dr. Santosh Pal, Dr. Kushal Singh, and Mr. Anjan Chakrabarti and R. Tirupati, and of course Suman Chakrabarti. Both have all of these students have worked hard for this work, And I would like to acknowledge my department, Material Science Engineering and IT Kanpur, and ACMS for the characterization tech facilities that they have extended, and of course the SERB DST for the financial support of this work. Thank you for listening for this talk. I can now take any questions.
Thank you, sir. We have few interesting questions from our audience. The questions will be displayed on your screen. Thank you, sir. We have few interesting questions.
So this is Siddharth Nanda, right? In NVP, the VO6 octahedra are randomly oriented, which inhibit the sodium ion diffusion. Can we consider substituting some other material in place of vanadium along with silicon substitution? Yes, you can do that. But you know what? Vanadium, we are having a 2, right? So we are exploiting that V3 and V4. So we have to use some type of element which is also a redox couple. Okay, that can either increase the potential because V3, V4 occur at 3.4 volts, and if you add some type of manganese or other transition metal, they have their own redox couple, and that will occur at certain other voltage. So there are few reports where you are trying to improve the potential of the cell, battery cell, by substitution vanadium along with the silicon substitution. But you can do that, of course. Yes, these electrolyte obstruct the dendrite growth, but the sodium metal is also reacting with the ceramic Nasicon electrolyte, where the dendrite growth or penetrate along the grain boundary. So that aspect we have not studied yet, but there have been some reports that this normally occur, where the dendrites form along the grain boundary, and then after a large number of cycles, there will be a short circuit as well. So there is a question from Priyadarshi. Sir, if we replace citric acid, any effect on reversibility, NVP, and connectivity? Yes, if you replace citric acid by some other type of another type of material, like you can use some type of acids which can provide you residual carbon, that will affect the amorphous and graphitic carbon present on the NVP particle. That will increase the performance or decrease the performance. But citric acid is widely known, and this has been said that this will provide you the best performance. But that will definitely increase or decrease the reversibility of NVP cathode. Thank you. Any other questions? So Usman mentioned that the slides are not clear. So can you let me know, Usman, what are the things that you are not able to see?
Rohit, this is Partha here.
Yeah.
Hello.
Hello, Partha.
Yeah. Hi. I have. It's a nice presentation on NVP cathode as well as solid state electrolyte for sodium and batteries. I have a couple of quick questions. What is the thickness of the solid electrolyte you achieved? Because achieving very thin solid state electrolyte is very challenging. So what is the
We
minimum
are
thickness?
doing our testing on 0.5 mm because higher, if we decrease the thickness, then when we are pressing the sodium, it's getting break.
So you cannot achieve more than 0.5, below than 0.5.
We have not tried it yet. But in 1-2 random experiments, we have found that it's breaking. The electrolyte are breaking. But we can try. We can use the tape casting and see how it goes. But the interface between the sodium metal and the ceramic electrolyte is a challenge.
Okay, very good. Okay, next
Either
question.
we have to go to high temperature to melt the sodium metal, and then there will be a good interface between. That we have not tried.
Okay. I was wondering on your NVPS cathode, what you mentioned initially. You mentioned that it's actually silicate anions replacing phosphate anions, right? PO4 is being replaced by
Yes.
SiO4. So, is it feasible? I mean, don't you think that silicon might goes to the vanadium or phosphor sites in the cation sites? I mean, this is looks to me a little bit challenging. What is your take on this? I mean, is it feasible? Like silicate anode
I
replacing
think
phosphate
I
anode?
think ionic radius is a major factor there, right?
Mm-hmm. Mm-hmm.
Ionic radius is a major factor, and we did the Raman, and we
Okay.
haven't seen any type of such type of bonds that is visible in that type of thing. So because
Yeah.
vanadium is around 0.7 around that, and silicon
Yeah.
is higher. It is
Yeah.
even
Silicon probably 1.0 maybe.
yeah, 1.0.
1.0.
And even if you dissolving this magnesium is a challenge because it's a very difficult to go maybe zero point 0.1, because magnesium and zirconium are having the same ionic radius, but
Yes.
putting
Yes.
silicon it will be too much actually.
Mm-hmm.
So we expect that it shouldn't be like that. But we also did XPS
Uh-huh.
there, and we haven't find any evidence where silicon can go in
Okay.
vanadium side.
Okay, very good. Last question. For your solid electrolyte, that's NaZB, you have doped with magnesium, and as you were showing the XRD, I can see some impurity peaks are coming, sodium phosphate, right?
Yeah,
So, do you think those presence of impurity is going to impair your performance, the full cell?
yeah. The
Because any kind.
if yeah, please go ahead.
Yeah, that's my question. Like, do you think that the presence of impurity will have an impact on your cell performance? Because any kind of impurity is going to, it's going to prevent the sodium and kinetics, and it will have an impact on the electrochemical performance. You did not address like how can you prepare phase pure solid state electrolyte.
So you see whatever the composition that we have prepared, it also have some zirconium oxide, right? ZrZb.
Yes, yes.
Okay,
Hmm.
so this is present in all the uh, composition that we have prepared. But as you add more and more magnesium, this Na3PO4 is coming there. Okay,
Okay.
and this
So
is
as you,
also this is basically thermodynamically like that. It will form this type of impurity. Now,
okay.
the good part is if we isolate these Na3PO4P phase, instead of spreading this Na3PO4 along the grain boundary, then it will definitely going to affect the ionic conductivity. But we are observing this Na3PO4 phase, and that will have some effect over the ionic conductivity. But how the distribution is, that is uh, we have observed it's only on the like a particle type. It's not a like a distributed like a glassy phase along the
Yeah,
grain boundary.
because your FESM micrograph shows nice crystals of the NaZB. It does not show where that sodium phosphate actually segregated and how it's
Yeah,
going to.
I have shown in the BSc image. It's a
Yeah,
small particles that are coming, but
yeah,
we are not able
okay,
to confirm whether it's a zirconia or Na3PO4 because zirconium and phosphorus have the same type of energy level, so it's hard to see. But computationally, it has been shown that Na3PO4 phase is formed, and normally we have observed these contrasting secondary phase only in the particle form, not on the like along the grain belt. So distribution of the secondary phase is going to affect much, and of
okay,
course it will affect the stoichiometry of the bulk phase. That will affect the grain conductivity.
okay. All right, thank you. I think for your presentation, just to stick around for a minute. Professor Mujumdar is going to felicitate you. Okay, just hang on
Okay,
for a minute.
so I have one question from Usman as well. Between solid and liquid electrolyte, which one will be considered more in terms high electrical conductivity performance? Of course, if you discuss, we have to choose between solid and liquid electrolyte in terms of ionic conductivity. It will be, of course, liquid electrolyte. Okay, because of course it's a liquid electrolyte. But for a safety point of view, you have to go for the solid electrolyte, and that's why the research is about go for the solid state batteries. So there is another question. I have seen a lot of papers and everyone is preparing NVPC using citric acid as a carbon source through solvent. Is it possible to prepare pristine NVP without citric acid? You need to have citric acid is playing two roles. It is providing the residual carbon. It is also acting as a chelating agent. Okay, to get a chemical homogeneity inside the material. Okay, so you can use you can prepare the pristine NVP, but you have to get some type of chelating agent. Okay, so you can use instead of citric acid some other type of tartaric acid or oxalic acid. You can use. You can try. Okay. Any other question?
Thank you so much, Professor Shobhit Omar, for your amazing talk explaining sodium vanadium phosphate-based cathode materials followed by solid-state electrolytes. I hope our participants must have understood the technical details related to solid-state electrolytes and sodium-ion batteries. Now, I kindly request Professor Ranabrata Majumdar to present memento to Professor Shobhit.
Thank you, Professor Shobhit Omar, for your very interesting presentation. And as a ceramist, we are also very much interested in that your solid electrolyte, these all solid batteries. So lots of questions on that. So from the organizing committee, we are presenting a small memento to you. So that will be sent you by post. So please accept it.
Thank you. Maybe sometime I will visit your department as well to see what are the works that are done in NIT Rourkela. Thank you.
Thank you all our audience. With today's session has come to an end, and we will tomorrow start again our day 3, session 1 with Dr. Vilas Shilke around 11 o'clock. Thank you.